Okay, hi. So today we're going to continue to talk about P-NP, and in particular, we would see a bunch of NP-complete problems. Last time we defined these classes P, NP, and we defined what it means to be an NP-complete language. And we sort of hand-waved and showed that there's one language called CircuitSat that is NP-complete. Okay, so I want to start by first recapping what we did last time, and then today what we're going to do in the hour and 20 minutes that we have is that we're going to see some other example of NP-complete problems. Some of them are maybe more natural. They are more combinatorial. They talk about graphs and things that are sort of similar to what we saw earlier in the course, but unlike the earlier problems that we saw, we don't believe that they can be solved efficiently. Okay. All right. So to recap, we were talking about languages and relations. And once you have a relation, which is just a collection of tuples, you can talk about the languages correspond to the relation, just all the inputs x, such that there exists a y, such that x, y is in the relation. The class P is the set of all languages that you can decide whether a string is in the language in polynomial time. So if I give you some string and ask you, is this string in the language L or not? You can write some algorithms that would run in time polynomial in the length of x and tell me the answer back. And we define NP to be the languages of relations such that the relations themselves can be efficiently verifiable. So what does it mean? It means that, if you give me both x and y, and we called y a witness, then there's an efficient procedure that can check that indeed x and y are in the relation R. But what's hard is given x to find a y such that y is in the relation. So we called it like the search problem that is associated with the relation R. And for many problems in NP, while it is easy to check for a given tuple if x and y are in the relation, it's hard for a given x to find a y such that x, y is in the relation. Okay, so this is like the difference between verifying and searching. Okay, or the difference, if you think about it, between searching for a needle in a haystack and recognizing whether something is a needle or hay, right? So these two things are very different. All right, and the big open question is whether P is equal to NP, whether P equals NP. And we also defined this notion of NP completeness. We say that a language L is NP hard if any language M in NP has a reduction from M to L. Okay, and I mean, reductions are something that we talked about for the last couple of meetings, but we also said that, to say that there's a reduction from one problem to another, you can also think of it as saying, that M is smaller or equal to L, right? That L is at least as hard as M. So a language is NP hard if it is at least as hard as any other language in NP, and it is NP complete if it is also in NP. So L is NP complete if L is NP hard and L is in NP. Okay, so that's a definition. Maybe we made this, we spend all this time making this definition. Maybe there's no language that is NP complete. It could be. I mean, we just made up something. And maybe there's no language that satisfies both these conditions. So surprisingly, there are some languages like that. And actually, there are thousands of natural problems or languages that are NP complete. And the first one is CSAT. We saw that CSAT is NP complete. Let me remind you what is CSAT. So first, what is a circuit? A circuit is a directed acyclic graph where we have, okay, so you can look at this example on the bottom. So we have variables at the bottom of the circuit, and then like all the arrows go up. Okay, so it's a diagram, so I can orient all the edges to go from, from bottom up. And every other vertex is marked with either an AND gate, OR gate, or NOT gate. Okay, so if you're an OR or an AND, you have two inputs, and if you're a NOT, you have only one input. Okay, so in particular, like this gate next to Y2, right? So this is the NOT gate, and it accepts only one input, Y2. This gate is an OR gate. It takes two inputs, like this gate and this variable. Okay, so these are circuits. Circuits sort of represent Boolean expressions or Boolean functions, right? In particular, this circuit represents this Boolean expression. It's Y1 or Y2 and Y2 not or Y3. Okay, so, and also let me mention that every circuit that we will talk about has only one output wire. So there's like one thing that goes, up to nothing, and this is like the output of the entire computation. Okay, so let's say that, let's see, for example, what happens here. So let's say that Y1 equals true, Y2 equals true, and Y3 equals true. What would be the output of this circuit? So I guess we can check it. So if all of them are true, so they're all equal to 1. So this Y would be equal to 0. Now here we have an OR of two things. So this would be a 1. This would be a 1 as well. And the end of a 1 and a 1 is a 1. Okay, so the output, if we take all the inputs to be 1, the output will be 1. So the circuit would accept this input. We say that a circuit accepts an input if given this input as an assignment to the input variables and propagating all the values up, we get a 1 at the output gate. Okay. All right. So what's the circuit satisfiability or CSAT problem? I give you a circuit on several inputs like Y1 up to Yn, and you need to tell me whether there exists an assignment to these variables that makes this circuit accept. Or in other words, there's an assignment that satisfies the circuit. Okay, in other words, whether there exists some string y in 0, 1 to the m, such that if I apply C on this string y, sort of I'm replacing all the variables with either 0 or 1, depending on the string, and propagate all the values up, then I get a 1. Okay, so that's the problem. Like, for example, here, we saw that there exists such an input, right? So we just checked that one of the one input and it worked for us. But in general, what can you do? You're given this circuit. One thing that you can do is just, try all possible strings of length m. There are 2 to the m of them. Try. Every time that you try, you just evaluate the circuit and you see whether it's 0 or 1. Maybe in almost all the tries that you're doing, you get a 0. So you need to continue because you cannot rule out maybe there's a 1 ahead in your list. And this is what we believe actually is the best that you can do for this problem. So there's no algorithm that works more efficiently than exponential time for this problem. Okay. I mean, not that we know of. It could be that there is one that we have no idea how it looks like. Okay, so the theorem that I sort of hand-waved last time is that CSAT is NP-complete, or in other words, that you can reduce every problem in NP to this problem about circuits. And like, let me remind you a little bit how this goes. So you think of some problem in NP, given some input X, you need to decide whether there exists some other witness Y, such that XY is in the relation R. So to encode this question, whether XY is in the relation R, you can encode it by some kind of circuit that sort of, at every point in time of the computation of the algorithm has like the entire state of the memory of the algorithm and all the registers and where, the next instruction would be. And eventually, we have layer per time stamp, and eventually in the last timestamp, we are checking whether the algorithm accepted or rejected, and this is would be the output of the circuit. So if you want to see it more formally, you need to know this notion of like what is a Turing machine, which captures basically every efficient computation. And once you have the language of Turing machine, you can do this thing formally. Okay, so this is covered, for example, in the course 172. Okay, so I wanted to mention one corollary, which is a simple corollary, but I think it's very important to state. And this is the following. So we established that CSAT is NP complete. So I want to claim that this is the same as saying that this question of whether P equals NP is equivalent to the question of whether there's an efficient algorithm for CSAT. Okay, so CSAT is in P if and only if P equals NP. If P is different than NP, then CSAT is not in P. Okay, so let's see both directions here. They are kind of simple. So we know that CSAT is in NP, right? So if P equals NP, then CSAT is in NP, but NP equals P, so CSAT is in P, right? So that's easy. The other direction, so let's assume now that CSAT is in P. Then what do we know? We know that for every language in NP, there's a reduction from L to CSAT, right? Or if you remember, what does it mean, a reduction? It means that there's like a black box solving L, where you do some pre-processing, and then you apply an algorithm for CSAT, and then, you know, if it says yes, then you output yes, and no, you output no. Okay, so notice that I'm like changing a bit what I mean by reduction. Now we are talking about reductions of languages, and actually this is the type of reductions that we saw. We showed that you know, an input, the reduction actually only has a pre-processing step, so it doesn't have any post-processing step in the proof that we showed for Cook-Levin. Okay, so let's now, so you assume that CSAT is in P, so can we also solve L in polynomial time? Well, definitely, right? Because we are doing the pre-processing in polynomial time and then applying the circuit SAT algorithm in polynomial time. So this means that if CSAT is in P, this means that L is in P. Okay, so all the languages in NP are also in P. So this shows that, you know, P equals NP. Okay, so this entire question about, you know, these two, you know, beautiful complexity classes, polynomial time on one hand, non-deterministic polynomial time on the other, whether they are equal or not, boils down to a question about a single problem, this circuit SAT. Can you solve this in polynomial time? Yes or no? If you cannot, then P is different than NP. If you can, then P equals NP. So it's quite remarkable, right? All the problems in the world, I mean, not on the world, but, you know, thousands of problems reduced to this one question. Okay. And now I want to move to today's topic, which is reductions between combinatorial problems. So this is a paper by Richard Karp, as you can see from UC Berkeley. He published this paper in 1972. It was 1 year after this result by Stephen Cook. This theorem that you know, you can reduce every problem in NP to circuit SAT was proved by Stephen Cook, who was also a professor at Berkeley at the time. Now he's at Toronto. But it was also proved in the USSR by Leonid Levin, now also a professor in, I think, Boston University. So it was proved sort of independently, like in both continents. And a year after Steve Cook result, Richard Karp came up with 21 problems, and he showed that all these 21 problems are NP complete. And these are like almost all the problems that you'll see in the book are in this one paper of Karp. And in particular, he introduced the notion of a reduction in this paper. So that's, I think, very nice. So he says, we next introduce a concept of reducibility, which is of central importance in this paper. He says that two languages L and M, sorry, that a language L reduces to M if there exists some function. So this means that this function is, this is, you should think of it as like the pre-processing. And to say that a function is in pi, you need to read a little bit above what it means, but it means that it's computable. Pi is everything that's computable with polynomial time. Okay, so there's some reduction computable in polynomial time, such that x is in the language if and only if f of x is in the language M. Okay, so, and by the way, this notion of a reduction has two names. So this is called many-to-one reduction. And it's also called a Karp reduction. So at least in Israel, we call it a Karp reduction. So, so what do I mean by this? So this is exactly like the picture in the previous thing. So you get some input x, and you want to check whether the x is in L. So you do some pre-processing. You apply some function f. And then you ask this, you ask this black box that solves the problem for whether some string is in the language M. And if it tells you yes, you output yes. And if it tells you no, you output no. Okay, so you better have it that whatever M answers is the correct answer for X. So you better have it that, X is in L if and only if f of X is in M. Okay. And in fact, like if you look back at the reduction, for example, that we did between Rudrata cycle and Rudrata path, this had this structure. Okay, in particular, there we also received like the object that we were looking for. But if we are just concerning whether there exists a path or whether there exists a cycle, then we can just, do no post-processing. We can just output what the black box told us. Okay. So Karp had this very nice picture in his paper, and he showed that, he started with circuit satisfiability or actually satisfiability, and then he reduced it to all these other problems, and he showed that all these other problems are NP hard. So that there are, you can think of it as if there are errors here, and every error means that there's a reduction. So this is a paper with many reductions. So notice that this is something that we talked about last time. Once this is NP complete, and you have a reduction from this problem, let's say satisfiability, to 0-1 integer programming, then also 0-1 integer programming is NP complete, right? Because there's like a reduction from every language in NP to satisfiability, and therefore by this composition of these two reductions, we get that there's a reduction from every language in NP to 0-1 integer programming. Okay, and today we're going to see some of these reductions. Obviously not all 21, it will take too much time, but we will see like a nice sample of those. Okay, and I think some of these reductions are also in the discussions, and one of them is in the homework. So I think this one is in the homework, for example. All right. So any questions about the, everything I said so far?
Feel free to raise your hands, but there are a couple in the chat that I'm worried I'm going to take out of context. Okay, there's a question that says, how does the CARP definition of reduction differ from what we already had?
Yeah, so what we had initially was something about, you have some kind of pre-processing and post-processing. Notice that in a CARP reduction, there's no post-processing. So in particular, I cannot run the algorithm and then look at the answer and maybe, if the answer was yes, say no. And if the answer was no, say yes. I cannot do that. And this is somewhat important because if I would be able to flip the answer, then suddenly this reduction doesn't preserve. So you could have something like that. Like if you can flip the output, then something like this would not imply, and let's say I know that M is in NP, would not imply that L is in NP. And the reason is that for NP, we really care about proving that things are in the language. We don't know how to prove that things are not in the language. So if we can flip the answer from the algorithm, then we can suddenly also sort of decide whether things are not in the language. Okay, so this is sort of like a subtle point. I mean, it's not something that we would go into. If you learn 172, it will be more important. The important thing here is that there's no post-processing. Okay, so when we talk about CARP reductions or reductions between languages, there would be no post-processing step. There's like an even stronger notion of a reduction called the Turing reduction, where you can think of it as if you're given access to a black box and you can ask this black box many questions, not only one. And maybe these questions can be adaptive. So maybe you'll solve one problem and then based on the answer, you'll solve another problem and so on and so forth. So this is, again, this is a reduction that does not preserve, the fact that, if one language is in NP, the other is in NP. But it does say that if one language is in P, then the other is in P. So, okay, so for this reason, CARP reductions are better when we talk about NP because they sort of preserve this. Okay. All right, so I should say that a lot of these reductions are very creative, and it's not that easy to come up with these reductions. So this is a seminal, celebrated paper, and I think it was one of the main reasons that Richard Karp got the Turing Award in the 80s. So this is really remarkable work, and after this followed, there are now thousands, or if not tens of thousands of problems that are NP complete. So if you draw a picture now, it will be probably a very big tree here. Okay, so we start here. I want to start first from the reduction from satisfiability or circuit satisfiability to satisfiability with at most 3 literals per clause, or this is also called FreeSat. Okay, so a much shorter name. Okay, so we want to show a reduction from CSAT to FreeSat. Okay, that will be the next goal. So let's first define what is CSAT. So FreeSat would be very similar to CSAT, circuit SAT, but the difference is that instead of talking about circuits and their satisfiability, we will talk about CNF formulas of very, very structured CNF formulas. So this is the definition of the problem FreeSat. So you are given a CNF formula phi on inputs, let's say x1 up to xn. So in particular, where each clause involve 3 literals. Okay, so what do I mean by that? So what is a CNF formula? It's like an end of ORs. Okay, so it looks like that, and inside, so each one of those is called a clause. And each clause has some variables or their negation. So let's say here it's like x1 or x7 or x15. Here it will be x1 not or x2 or x3 not. And then we'll have, I don't know, x3 or x4 or x7 not. Okay, so you have a bunch of these constraints. Each constraint involves three variables or their negation. A variable or their negation is called a literal. And your goal is, you need to decide whether there exists some x in, let's say, 0, 1 to the n that satisfies the formula. Okay. In other words, you need to decide whether there is some assignment to the variables, these n variables, so such that each clause is satisfied, right? In order to satisfy this entire end of clauses, we need to satisfy each clause individually. And each clause involves three variables. So particularly, we have to have that either x1 is 1, or x7 is 1, or x15 is 1. We have to have it that either x1 is 0, x2 is 1, or x3 is 0, right? So we have a bunch of these local constraints. Each one of them involve three variables, and we want all of them to hold simultaneously. We want to know whether there's a way to satisfy all of them. So you can think of them as like some kind of constraints that we have about Boolean variables, and we want to know whether we can meet all of the constraints simultaneously. Okay, so in particular, you can see that this is like a special case of circuit SAT, because I can always write this expression as some kind of circuit, right? Just an AND of ORs. And I can, so it's a special case. If I want to, I can make it into a binary tree, right? So if I have like an OR of three variables, I can convert it to the OR of I'm taking the OR of the first two, and then taking the result and taking the OR with the last one. Right, so I can always convert like this expression into a circuit. So that's a special case. So obviously, free SAT reduce it to circuit SAT, but that's not interesting because we already know that everything in NP reduces to circuit SAT. I'm just saying that the reduction here is kind of simple. Like free SAT is in some very straightforward way can be reduced into a circuit SAT, where we can write this expression as a circuit, as a smooth circuit. Okay, and I sort of need to introduce, like when I take the OR of three variables, I need to introduce intermediate two gates in order to compute it with a binary tree, or a binary, with gates that have Fanning 2. Okay, so that's like an easy and not that interesting, but what is more interesting is to show that there is a reduction from CSAT to free SAT. Okay, so if you want to solve satisfiability on general circuits, it suffices to solve satisfiability on these expressions that are very structured. They're like an AND of many clauses where each clause involves only three variables. Okay. So notice also here, like what would be your strategy? How would you solve free SAT? If you have a good idea what an assignment is, you can check whether it's a good assignment or not, right? So once you have an assignment, checking whether it satisfies this formula or not, this you can do in linear time, in the length of the formula. But maybe you'll need to go over all possible assignments before you find one that satisfies this thing. And there are some algorithms that are running less than 2 to the n time, but the best runs in like time, I don't know, 1.4 to the n. So we don't know how to solve it in time, which is less than 1.1 to the n. Okay, so And I want to say, you can change this problem and tweak it a bit. What if in every clause you had 2 variables instead of 3? Or 4 or 5? Okay, so if you have more than 3, then this is definitely at least as hard. And if you have 2, actually it becomes easy. So 2SAT is a problem that can be solved in polynomial time. Yeah, I'm not sure that we'll have time to go over it, but there's like a very simple algorithm that involves, you somehow find a graph that is corresponding to these variables, and you check whether there's like a path from a variable to its negation or something like that. And if there's no such path, then you know that you can satisfy 2SAT. So there's an algorithm if you're talking about 2SAT. For 3SAT, it's NP complete. Okay, so I want to show you this reduction. Any question about the definition of 3SAT?
Yeah, there are a few questions about whether or not each clause has exactly 3 literals or at most 3 literals, and how to get around that.
Yeah. So let's say, like in our definition, it will be at most 3. I think you have an exercise about getting from at most 3 to exactly 3. So I would not solve you the homework here. But yeah, so you can talk about the 2 variants. So we will talk about the variant where you have at most 3. So it's most 3.
And then there's also a question, what does conjunctive normal form mean? But I don't know if that's important to this.
I mean, it's just what I like this example, right? Conjunctive normal form is an end of ors. Okay, so that's just it. It's a fancy name for this, for this thing. There's also DNF, which is like an or of ends, if you like. Okay, so let's just give simple example. So let's say phi is this formula, this CNF formula. Yeah. Okay. So is there a satisfying assignment to this formula? Okay, so that's an example from the book. So maybe you've read about it already. And the claim is that there's no such assignment. But let's see how can we be convinced of that. So let's just focus first on these 3 equations. What do these 3 constraints mean? They are 2 local, right? So they involve only 2 variables. So in particular, let's just start by we need to decide the values of these variables. So let's check if there's an assignment where x1 equals 0. Okay, what would happen if x1 equals 0? If we want to satisfy this entire equation. Okay, so I'm like looking at this. You can think of it as some kind of backtracking algorithm that I'm trying to do in order to decide whether this formula is satisfiable or not. Okay, so if x1 equals 0 and I want to satisfy this thing, then this literal x1 is not satisfied, so I must satisfy the other literal x2 not, right? So this means that I have to fix x2 to 0. But if x2 is 0, then this literal is not satisfied, right? So I must satisfy the other literal, so I must also fix x3 to be 0. But then I have a full assignment, 0, 0, 0, and I notice that this assignment doesn't satisfy the first clause. So this is not satisfiable. Okay, so this path does not satisfy. Sorry. Let's say reject. Right, so the circuit rejects this assignment. Okay, we still have another path that we haven't checked. So what happens if x1 equals 1? Well, notice that now this variable, x1 not, this literal is not satisfied. So therefore, we have to satisfy x3, right? Okay, so we have to satisfy x3, then this literal now will be 0. So this means that we have to satisfy x2. But then we got 1, 1, 1, and this does not satisfy the last clause. So we reject any in this case as well. So we sort of argue that there's no way that we could make this entire thing satisfiable, right? So by going over more or less all, all possibilities. Okay, so this was an example where you cannot satisfy the formula. In general, this problem of SAT is it's maybe like the first and most important problem that is NP complete, and there are a lot of there's a lot of effort to come up with good heuristics and good algorithms for that works on in general in practice, and these are called like the SAT solvers, if you heard about them. And the reason that they are so useful is that when you're like writing when you're trying to verify that your CPU is doing what it's supposed to do, you can write some kind of SAT formulas to say that something bad doesn't happen, and then you want to check that they are indeed always true, right? So this is sort of very important in verification and in a lot of other applications. So SAT solvers are used all in the industry all the time, and SAT is a really important problem. Okay, so now we want to show that circuit SAT can reduce it to free SAT. So I want to do this reduction by an example. So let's say that I give you the following circuit. Okay, so it'll take me some time to write it. So by convention, I assume that all the arrows go up. So like a gate is fed by the two gates below it. Okay, so let's say that I want to know whether this circuit is satisfiable or not, whether there's an assignment that satisfies, that makes this circuit output 1. How can I write this question in terms of, free CNF or free SAT? I want to check whether there exists, I want to write a formula that is like the end of many, clauses where each clause involves only 3 variables. Okay, so the idea is to introduce new variables. So we would have these y1 up to y4, but we would have additional variables that are new that we introduce in this reduction. And what would be these variables? They would correspond to each of the gates. So let's call this variable Z1. This would be like the value of the gate, this output gate. Z2 would be the value of this NOT gate. Z3 would be the value of this OR gate. Right, so we have 6 gates, so 6 variables. And now I want to say, right, I want to ask, does there exist a sequence of Y's and Z's such that the Y and Z are consistent with one another, meaning that the gates really compute what they should compute. This gate outputs 1, and that's it. So that's what I want to encode. So I want to ask whether there exists some assignment to the Y's and the Z's such that Z1 equals 1. And in addition, Z1 equals Z2 and Z3. And in addition, Z2 equals Z4 not, and Z4 equals Y1 and Y2, right? So on and so forth. So I'm writing like one condition, one constraint per gate. Like every gate, I want to check that its value is consistent with the two wires that feed into it, right? I have two inputs, let's say for an AND gate. So I need to check that these two inputs and the value of the gate are consistent with one another. Okay? So once I write this, I claim that this circuit is satisfiable if and only if this equation is satisfiable. Okay, and this is sort of easy to convince yourself. If there's an assignment to the y's, then there's also an assignment to the z's that satisfies this formula. And this is sort of an if and only if, right? The only way that we can find an assignment to this formula is if we can find also consistent computation on the circuit. Okay, so I mean, I'm not writing in words, that these two things are equivalent, but they are. But notice that this is not a CNF, right? So here I wrote it in some kind of the constraint in some language, like, right? I said, Z1 equals Z2 and Z3. This is not like an OR of three variables, right? So I need to convert all of these constraints involving three variables into CNFs. And there's always a way. So if you have some kind of Boolean predicate or Boolean expression involving only three variables, you can always write it as a free CNF. So that's sort of something worth knowing. I don't know if you've seen it before, but you can sort of write, if you have some, let's say that you have some three variables, I don't know, A, B, and C, and you have some function on them, some expression that, and all of them are Boolean. So I can write the entire function as some kind of truth table, right? So I just need to specify what the value of this expression is on all possible 8 Boolean strings. So maybe it's like this function is something like this. Okay, and now the question is how to write this function or this expression f, how to write it as a free CNF, as an AND of clauses where each clause involves three literals. So how can I do that? I can write for every line in this truth table, I can write every line for which the value of the function is 0, I can write a clause that rules out this value. Okay, so here I would say, A or B or C. If all of them, if A is 1 or B is 1 or C is 1, then I know that I avoid this line, right? Similarly for here, I can write, A or B or C naught. This tells me that I'm avoiding this line. And here I can write A naught or B naught or C, okay? And if you take the end of all these three clauses, then this would actually compute the function f. Okay, so I claim that f equals this and this and this. Right, you can check for yourself. Let's say that you give me three Boolean variables. If they fall into one of these three lines, right, then let's say that I fall into this line, then it means that this is not satisfiable. Like if I fall into the first line, then it means that this first clause is not satisfiable. So I would get a 0. But if they fall into one of the other lines, then they satisfy both three constraints. Okay, so if you are not familiar with it, it's worth knowing this fact. But I can also give you some kind of, like a cheat sheet of how to convert these things. So for example, let's say that I want to convert this expression Z2 equals Z4 naught. Okay, so I claimed, okay, I did my homework and I checked how to convert it into a CNF form. And the way to convert it is to say Z2 or Z4 and Z2 naught or Z4 not. Okay, so these two things are equivalent. Let's see that they're equivalent. Let's say that I don't know, Z2 is 0 and Z4 is 0, right? Is it correct? Right, so if Z2 is 0 and Z4 is 0, then this is not satisfiable, right? And on the other hand, this is also not satisfiable. What would happen if one of them is 0 and the other is 1? Then this would be satisfiable because one of them is 1. And this would be satisfied because one of Z2 and Z4 is 0, therefore its negation is 1. So you can see that these two expressions are equivalent. You can also find expressions for if you have something like G equals H1 or H2, then you can write some expression like this is equivalent to G or H1 or H2 and G or H1 or H2 not. And you can further open this up, and this the first thing is already a clause. The second thing is not a clause, but you can write it as it's like G or H1 not and G or H2 not. Okay, and you can check that these conversions indeed work, and you can do something similar for AND. Okay, so the point is this. So let's zoom out a little bit. So we have this circuit, right? We just want to check whether it was satisfiable or not. We introduce these intermediate variables, sort of capturing what the value of each gate is. And then once we had these intermediate variables, we can write local constraints that only involve either 2 or 3 variables in each constraint. And then there's like a very mechanical way to convert things that involve at most 3 variables into 3 CNFs. Okay, so it's sort of like by brute force, you can think of it. In the end, we get that there's a 3 CNF formula such that there's a satisfying assignment to the formula if and only if there's a satisfying assignment for the circuit. Okay. Now I can tell you there sometimes people also present a reduction from satisfiability on general CNFs to satisfiability on free CNFs. I want to claim that this is just a special case of this reduction that we saw. So let me show you also this reduction. So usually when people say SAT, they mean that it's like SAT on CNFs. So it's like, you get an equation. Sorry, you get a formula like this. So it's in CNF form, but you don't know, like the length of clauses is unbounded. It could be like more than 3. It could be square root 10 or something like that. Okay, where we have n variables. So how do you convert this question of satisfiability on CNFs to the question of satisfiability on free CNFs? So in some sense, you want to take like take a clause and to convert it into some kind of an end of smaller clauses, right? So that's like what you would like to do. So you can think of this. So let's look at like this clause. So let's say there are like 5 variables here. So if you think of this clause as a circuit, how would this circuit look like? It's something like this, right? So it's like the OR of these two. Then I take the OR with x3, then the OR with x4, and then the OR with x17. right? So if you introduce now variables for each of these intermediate gates, okay, so then you'll see that you have this expression. So you need Z4 to be true. You want, you know, Z3 to be equal to, sorry, Z4 to be equal to X17 or Z3, right? So on and so forth. And this you can convert, this is equivalent to saying that, you know, if X17 or Z3 is true, then okay, so I might have some details missing, but in any case, when you open it up, there's a very nice expression that you would get, and it's of sort of, okay, so maybe let me do some kind of you know, dot dot dot. What you would get is the following. You would get the formula that you get is something like this: x1 or x2 or z1 z1 naught or x3 or z2 z2 naught or x4 or z3. I think it's something like this. Maybe I made a mistake. Sorry that I'm not prepared. But the main point is that, you know, you can get this reduction from SAT to free SAT. You can get it just by going from the circuit SAT to free SAT. And you just convert one clause. You represent it as a circuit. You introduce these intermediate variables, and you know, you write this free CNF for these intermediate variables. And you know, here maybe you can argue more quickly why this is satisfiable if and only if, you know, this entire clause is satisfiable. Yeah, so if the entire clause is not satisfiable, then all these x's, you know, if an assignment for x satisfies this clause, then I claim that there is no choice for the z's that would make it satisfiable. So this is because if all the x's are false, then we must pick all the z's to be, I guess we have to pick all of them to be true, and maybe, okay, so sorry, so maybe here I have z4 not, and then this would make this last clause false. I'm sorry, I'm skipping some details here. I thought that it was very simple, so, but I see now that there are some details missing here. But anyway, there's also a reduction that is more direct from SAT to free SAT that I sort of presented here with some bugs probably. So it would be better if you see it in the book. Okay, so all right, so far we discussed about satisfiability. So we showed that circuit SAT, right? So this is what we showed so far. Now I want to go to problems that involve graphs. So this will be a little bit more familiar with other things that we saw earlier in the class. So I want a reduction from free SAT to independent set. What is independent set? So you are given a graph G. and an integer k, you need to decide, is there an independent set of size k in G? What's an independent set? Independent set is a subset of the vertices such that no two vertices have an edge between them. So we are looking, we have some graph. I don't know, let's say this thing. And we're looking for the subset of the vertices, let's say this one and this one, so that they don't have any edges between them. Okay, so this is, for example, an independent set, these two vertices. Okay, and this seems like a, you know, very, fairly simple question, right? I give you a graph, find me, and I give you a number, find me a set of, you know, k vertices that have no edges between them. At least it's a problem that is easy to think about or easy to describe, but it turns out this is an NP-complete problem. So, okay, so the theorem is that independent set is NP-complete. So let's see, you know, let's see why. So the first thing is we need to show that the independent set is in NP. Why is that? So that's like the usual, like the easier direction or the easier step that we need to establish. So why is it the case that independent set is in NP? If I give you the graph in K, what would be a relation that would sort of recognize whether this is an instance of independent set or not, right? So the input, recall, is like this tuple, like both G and K, that's the input. So the relation would be on inputs G and K, the output would be the set S such that S, is a subset of the vertices. It's of size K and independent set. Right, so this relation is recognizable efficiently, right? I can verify it efficiently. If I give you the subset, it's easy to check whether it's a good subset or not. You just check that all the pairs don't have any edges, right? The hard thing is to find this subset. So this is the relation that proves that this problem is in NP, or in other words, you can think of it as follows, this S is a witness that the graph and K are indeed in the language independent set, right? So there's a short witness that can be efficiently verified, this subset S, that can prove to us that a graph has an independent set of size K. All right. So that's just to make sure that we are on the same page and to make sure that this problem is in NP. And now to the more interesting proof, why is it in NP complete? Okay. So now we will see a reduction that goes from SAT or free SAT to independent sets. Okay, so we will see a reduction like this. And this is quite interesting because it's sort of like connecting two domains that seem to have nothing to do with one another, right? So free SAT is sort of about circuits, formulas, and Boolean variables, whether there's an assignment that satisfies all of them. Independent set is asking something about graphs, but these two problems are related. There's a reduction from one to the other. If you can solve one efficiently, you can solve the other efficiently. Okay, so let me show this reduction again by an example. Okay, so let's say that I have this I have this CNF formula, or rather free CNF formula. Okay, and I want to come up with a graph and a number such that if this formula is satisfiable, this graph has an independent set of this size. And if this formula is not satisfiable, then this graph doesn't have an independent set of this size. Okay. So the idea is to take every clause and come up with a small gadget, like a small set of vertices and edges that correspond to this clause. Okay, so this is like the first step that we do. So we'll take this clause and we'll introduce like a triangle that corresponds to this clause. So we'll introduce 3 nodes and we're going to label them. So one of these nodes would be labeled by X. Sorry, I want to be consistent with my notes. So let me do it. Okay, so I'm introducing like three vertices per this clause, and then I'm connecting all these 3 vertices with edges. And the idea of why I'm connecting them by a triangle is that when I'm looking for an independent set, I can pick at most one from a triangle, right? So if I pick this vertex to the independent set, I cannot pick any of the other 2, right? Because they are connected to both. They're both connected to Y. Okay, so I'm doing the same thing for every clause. So here I have X, Y naught, and Z. And here I have X, Y, Z. And here I have X naught, Y naught. But notice that, so far I just introduced like either a triangle or, an edge per each clause. But in some sense, and I gave them these labels, but these labels don't mean anything, right? So I don't, right, in the question about independent set, I don't really care about the labels of the vertices. I just care if there's an independent set. So the labels are sort of some sort of bookkeeping that now I'm going to use. So now I'm going to, add edges between every vertex that is marked with X and every vertex that is marked with X complement, X bar. Okay, and the idea is that I don't want to pick both the vertex that correspond to X and the vertex that correspond to X bar. I don't want to pick both of them to the independent set. So by putting an edge, I'm sort of enforcing a constraint that in the independent set can choose at most one of them. And saying, okay, so I need to add these 4 edges between X and X bar. These edges between Y and Y bar. And between Z and Z bar, I have this edge and this edge. Okay. And now, so I got this, graph G, which is, it's a graph that depends on this formula phi. So I denote it by G of phi. And I'm going to ask, whether this graph G phi has an independent set of size 4. So let me write it like that. Whether this tuple of the graph and the number 4 is in the language independent set. And, I need to, in order to show that the reduction is indeed a good reduction, I need to show that phi is satisfiable if and only if G phi 4 is in IS. Okay. And in general, you know, I will just, you know, take every clause and put a triangle or an edge, depending of whether I'm talking about 3 variables or 2 variables. And I'm going to introduce edges between every vertex that correspond to a variable and its negation. Okay, so if we prove this claim, then we prove that this is indeed a reduction. Notice that this is a polynomial time reduction, like the conversion that we described is very efficient given the formula, right? So this is a claim that I want to prove. Okay. So let's see the first direction. Okay, so it's an if and only if claim, so I want to show it in both directions. So if phi is satisfiable, right? So I want to come up with an independent set of size 4 in this graph. So how would I pick this independent set? So phi is satisfiable. It means that in every clause, there exists a satisfiable, sorry, okay, so fix an assignment A that satisfies phi. Okay, so there's some assignment to the input variables so that every clause in phi is satisfied, right? So this A is some you know, vector in 0, 1 to the n. And now how I'm going to pick the independent set based on this assignment. I know that in every clause, there exists at least one variable, sorry, one literal that A satisfies, right? So if we go back, sorry about going back and forth. So let's say that we pick some assignment, I don't know, that satisfies this entire thing. It's hard for me to come up with it on the fly, but let's say that 0, 0, 0 is such an assignment. So I look at like this first clause, we have to have that at least one of these variables is satisfied by this assignment. It could be that maybe more than one of them, but I'm going to pick only one. So I'm going to pick only one literal that is satisfied in each clause. So pick exactly one literal in each clause that A satisfies. Okay, and I claim, right, so and each of these literal is corresponding to some vertex in the graph G pi, and I claim that this set of vertices is an independent set. Okay. So why is that the case? So one thing, so we picked only one per triangle or per, you know, these, you know, mini clouds that we introduced. Like you can think of it as if we introduced like a small cloud of vertices and edges per clause. So we picked at most one per clause. So we don't have any edges between right? So we don't have any edges inside these clouds, right? So let's say here we pick like this one. Here we picked, I don't know, maybe this one. I don't know, maybe something like that. So we picked at most one per cloud. And another thing is that we didn't pick, right? So we picked it according to the assignment. So what does it mean? It means that if we picked X, we couldn't have picked X bar, right? Because the assignment does not satisfy both the literal X and the literal X bar. It satisfies exactly one of them, right? So if the assignment is 1 for X, then it satisfies X, but it doesn't satisfy X bar. So for these reasons, this is an independent set because we don't see any edges inside these triangles, and we don't see any edges between the triangles. Okay, so this is sort of by the construction. Okay, so this was the one direction. What about the other direction? Right. So recall that when we prove that a reduction is a good reduction, we have to prove that this is an if and only if, right? That the reduction maps yes instances to yes instances and no instances to no instances. All right, so now let's assume that this graph G has an independent set of size 4, right? What do I need to prove? I need to prove that the original formula had a satisfying assignment. Okay, so let S be an independent set of size 4 or M. Okay, so M is the number of clauses, right? So in this case, it's 4. In G prime, I want to, from S, I want to come up with some assignment to the formula phi. So I'm going to look at all the variables or all the literals that appear in the vertices corresponding to S, right? So by the way we constructed this graph, okay, by the way we constructed this graph G, we know that S has at most one vertex per, let's say, cloud or triangle, right? So that's just because S is an independent set, so you cannot pick 2 vertices in the same triangle. So in particular, so what does it mean? It means that in every triangle we can pick at most 1, and we picked, you know, m many vertices, so we must pick 1 per triangle. Okay, so we picked exactly 1 per cloud. And now I want to come up with an assignment. So for each vertex V, right, I have some label of this vertex. It represents some literal. So what I'm going to do, I'm going to assign the relevant variable to satisfy the literal. Okay, so let's say that, you know, so let's say that the independent set is, I don't know, maybe this thing. Okay, this is not good. Do you see a satisfying assignment for this formula? I guess it's a good question.
0, 0, 1.
0, 0, 1. Okay, 0, 0, 1. Okay. Okay, so this is like an independent set in this graph. Okay, and notice that I can, get from this independent set, I get the fact that, I want the x to be assigned to 0 and I want z to be assigned to 1. So this gives me some partial assignment in this case, because for y I didn't really say what I need to set it to. But this partial assignment already satisfies the formula. So I can pick y however I want. It could be 0, it could be 1. Both of them would satisfy the formula phi. Okay, so this gives the partial assignment, or maybe even a complete assignment, but in particular partial assignment that satisfies the formula. Okay, and so there are a few things to check. So why does it give a consistent assignment? The reason they give a consistent assignment is that, right, we have edges between everything marked with x and everything marked with x bar. So we wouldn't have this collision that we would say you have to assign x to 0 and you have to assign x to 1. This would not happen. And the reason that it satisfies the formula is because we have exactly 1 per cloud. So this means that the corresponding literal is satisfied by this partial assignment. So therefore, the corresponding clause is satisfied by this partial assignment. Okay. All right. So this completes the proof that independent set is NP complete. Let me give you, since I want to give you, one or two more examples, I want to give you one that is maybe an easy reduction. So the click problem is the following. You are given a graph and a number, and you want to say whether there's a click of size k. What is a click? It's a set of vertices such that every two are connected with an edge. Okay. The vertex cover problem is given a graph G and a number k. Either a set S subset of the vertices of size k such that S touches all edges in G. Okay. And I claim that these two problems are also NP complete. Do you see why click is NP complete? How can you, do you see some other problem that we already discussed today, that there's a reduction from this problem to click? What is click? Click is that you have, k vertices and all of them are connected. Right, so independent set, and the reduction is very simple. So from independent set to click, you just take gk and you output, let's call it g bar k. What is g bar? If g is ve, then g bar is ve complement, where e complement is just, if there's an edge if there's an edge in E, there's no edge in E complement and vice versa. So you just, reverse the graph. So every edge that there was there, you put no edge between. If there wasn't an edge between UV, then you put an edge there, right? So this sort of converts between things that the dead end between them now have no edge between them. So independent set corresponds to a click in this new graph G complement. So this is just all the pairs. Right, so it's a very simple reduction, and it's a very simple way to show that this is indeed a Karp reduction, right? The GK is an independent set. if and only if G complement K is in clique. And with respect to vertex cover, there's also a simple reduction. You don't need to change the graph at all. You just need to change the parameter. So it turns out that a set S is an independent set if and only if the complement set is a vertex cover. Yeah, this is called vertex cover. Where vertex cover, I mean that it's a collection of vertices that cover all the edges. So this is a simple claim that you can check for yourself, and therefore, to go between these two problems, these are basically the same problem in disguise, right? So you just, in order to check if there is a small set, if there is a set that O's members don't have edges between them, it's sort of equivalent to ask whether the complement set is a set of vertices that touches all the edges. Okay, so these are examples of like simple reductions, maybe simpler than the one that we saw earlier. I think like another simple reduction is between FreeSat to integer linear programming, and I think this is on your homework. So check it out. Yeah, so there's like a huge literature about these reductions between NP-complete problems. I recommend to you to look at more examples in the book. It's good to also try to solve a few of these and think of these reduction on your own. Some of them sort of require some creativity. I can tell you myself that I lost like 30 points in an exam because I couldn't come up with a reduction. So it's not always easy to come up with these things. But the more you practice, the better you get at it. So, all right, so I guess we are out of time. So let me finish here, and I'll take questions after we stop recording.